recording. There we go. So this one will be 20 north of east. If we have another vector there, and we want to know what our actual heading is, and I tried to draw that as being closer to the north than the west, but I think I failed. Let's go ahead and we'll start with this angle. So if we're looking at this angle, we're starting at the north and going towards the west to get to our vector. So this would then be going west from north, or you would be west of north. What if we wanted to do the complement and we wanted to start here and go to there? Then that angle, we start in the west, we go to the north, we are north from the west, so it's north of west. And maybe using that from, if you're struggling with this, is a good idea. You know, thinking about the fact that you're starting here and you're going.
So it's always going to be the first direction.
Okay, so here's another, and this is also going to be a compass rose problem. So we were indicating which direction is north. We can start from either side of this vector. We just can't start from the vector itself. So pick a cardinal direction to start from. Go for it, Katie. Pick one.
South.
South. Okay, you got beat to the punch. So we're going to start from the south. We're going to go towards the what? West. So we are west from the south. We are west of south. And we'll say this is 43 degrees. I have no idea how many degrees that actually is. Yeah, it looks reasonable. Okay, so now can we identify it from the other angle? Katie. So let's start from the west. What do we do?
When I'm looking at this, I understand that. But what I'm saying is when you're looking at the paper.
We went towards the south, so we are south from the west. This would be, let's say, what, 47 degrees south of west. Does that help make, if you were unclear on these, are you clearer? So the other question people have is, you know, when I have a vector here and let's say a vector there, and I'll move this whole thing over, and I know that my resultant is here. How do I know which angle? How do I know if I look at this angle or this angle? Is that the question?
No.
Okay. No? When you make your resultant is always going from the tail of the first vector to the head of the last vector. So here's the tail of your first vector, here's the head of your last vector. So we know that the resultant is going this direction. Does that make sense?
Yeah, we get it. Like, I thought you needed like.
And to figure out where we're starting our little helper arrow from, you have to always start from a cardinal direction. You can describe this angle, or you can describe that angle, but you have to start from a cardinal direction. You cannot start from the vector itself. Okay, now let's talk about this. Let's talk about green grass and happy fields of whatever. Okay, we have some sort of motion like this, running along the ground, leaping up into the air at some angle. We don't know what angle. That's the ground, believe it or not. Nowhere in this problem does it indicate north, south, east, or west. And these are the ones that get people the most confused because, believe it or not, north is not up, south is not down, west is not, that would be left, east is not right. That's our convention on maps, but it's not reality. So when you have a problem that has something like the ground and then up into the air, your resultant vector, your heading, is above the horizon, above the ground, But this angle is with respect to the ground or the horizon. And we get a lot of these. We also get things, especially later on in this chapter, where we have buildings with oddly shaped windows, and we have people like superheroes. I thought so. Who leap off of buildings. And we find their resultant displacements. So what's the angle here? No. Backpedal, backpedal. What? Something below the horizon, yeah. So in these, we're using the horizon as a reference point. In these kind of things, we're typically using the horizon as a vantage point. Let's do one more with the horizon, and the question is, what if you have something that's going like straight up in the air, and then it gets pushed in some other direction? So we could do a rocket, for instance, with that. So let's do one more horizon example that I will tell you shows up here. We have a rock in the water. Can anybody identify what this organism is? It's some sort of seal or walrus. It's a large pinniped. It's a pretty ugly pinniped, but we'll deal with it. No, this is the rock it's on, but thanks. So the pinniped dives into the water and then dives a little bit deeper. And from its starting point here, we want to figure out its resultant. And we can figure out magnitude, of course. But for heading, how could we describe that heading? Yeah, below the water surface is a typical point of reference. So we look at the water surface, and we think about making an angle between the surface of the water and the resultant. Does that help on these? Really, these things are situational. There's one problem that I don't know if I assigned it yet or not, but it's for you soccer players. It's a soccer field. And somebody kicks a ball, passes a ball one direction to somebody else, and then they kick it, yeah, something like that. And what's its resultant? And I think your book, and this is where, for some of these, you do actually have to kind of develop your own language for them. And like there's one, the soccer example is one where the book gives this, what I think is this horrible, horrible, horrible reference. And it's like 15 degrees something of upfield. I forget what the answer is, but it's stupid. And, you know, I would think you could come up with something better, like 15 degrees towards the end zone of, I don't know. I forget how they express it, but it's bad. And as we get to problems like that, we'll talk more about it. Let's talk about the example that somebody asked about with a rocket. There's a rocket. It's going to blast off. Lots of flames. I should shrink it. I do enjoy the drawing things on here. I really do. So if this rocket goes up and then, you know, curvature of the earth or winds or whatever cause it to do this. Is this kind of what we're asking? Okay. How, whoops. Curvature of the pen. Okay. How do we describe that trajectory? We can still use the horizon. There's no reason we can't use the horizon here. It is the most, it might look not obvious, but if we think, well, this is the horizontal, I mean, it's the larger angle, and I said typically we try to use the smaller angle, but in this case, you know, what else are you going to say? You know, right or left of straight up? I think your book actually does that for one. I think it's a stupid frame of reference.
Like right or vertical.
Yeah, it's something like that, you know, and they use like clockwise of horizontal, things like that, which it makes more sense to me than right and left, but that's just my little handicap. Anytime I can use the horizon, I do, because the horizon is a stable reference point. You know, 96 degrees above the horizontal. Well, yeah, is that closer to vertical than horizontal? Yeah, it is. Or 86 degrees above horizontal. Yeah, you're 4 degrees off of vertical. Could you say 4 degrees towards the ground from vertical. Yeah, you could.
Are you going from the horizontal to the vector?
Yeah, so here, if I use the angle that I just drew, I would say, whatever that is, 60 degrees above the horizon. Could I say 30 degrees towards the ground from straight up, from vertical? I could. I think it's klutzier, but it's not wrong. Yes, sir. Yeah, that's a good question. So the question was, is there something that you can do to make it clear that it's going this direction and not this direction from the horizontal? Yeah, and that probably is why the book sometimes uses the vertical. And here if we say this is 60 and this is 30, they would say 30 degrees clockwise of vertical, because that pegs it as being this 30 degrees, not that 30 degrees. So, yeah, good point. So yeah, there are lots of ways to figure this out. And like I said, for most of these vectors, there is more than one correct way to describe the angle. You just have to make it clear. What we can do with vectors, what you have done so far is called solving vectors. So when you solve for a resultant vector, you take the contributing vectors and you find the resultant. You use a tangent, an inverse tangent function, to find the heading. Can you do this in reverse? Can you take a resultant vector, so let's say we have this, and can you break that down to figure out how far you traveled in each direction? Yeah. This is called resolving a vector. So this is the opposite process. And what we say is that this is resolving it into its components. So when we take the resultant vector, and that's all we're given, and we resolve it into component vectors, it's just the opposite. Now, if you only have one of these things, if we go back to naming these as the resultants, and assuming that this is displacement 1, displacement 2. If all we have is the resultant, can we use Pythagoras? No, it's 3-part algebra. You can't do 3-part algebra unless you have 2 parts. So what tool do we have that will get us the components? Don't yell it out. Compare notes with someone sitting near you. What would be your immediate thought, your go-to tool? Too loud. Yeah, this is trig. This is gonna be straight up trig. So trig review. Would you like to do the Soka-Toa chant? Do you need to get the blood out of your butts? Do you want to stand up and stomp and let Mrs. Haylett know that we're awake and doing things? So is sine opposite over hypotenuse. Sine equals opposite over hypotenuse. Ka is. Go ahead, you can do it too. Adjacent over hypotenuse. Toa is Krakatoa. I know, I always think of Krakatoa too. Tangent equals opposite over adjacent. Okay, and we'll get into some trig functions in the next week or so. I'm sorry, trig identities. All right, so and ka and toa, well, what we have here is a resultant vector. So where is this kind of thing useful? Well, it's really useful if we know that we went 23.5 meters at 15 north of east, and I want to know how far north I am. How far north am I? Am I farther north than I am east? Am I farther east than I am north? So to resolve this into its component vectors, we have to look at something. So what I've done is draw in the component vectors. And color coding, especially if you're a really visual learner, color coding helps. I tend to, when I'm doing vector analysis, especially when it's bigger, hairier vector analysis, I get out the colored pencils. Using Doceri, see ya. It's easy because you can color code all your lines. I literally color code my calculations. And when I'm doing it on paper with colored pencils, I'll do the calculations in pencil, but then I'll circle all the calculations that apply to a particular vector in the color of the vector, because it's a visual cue for me and I don't screw things up as much. Okay, so from this angle, which side is the opposite? Yeah, the y-axis. So if I had said earlier that this was D1 and this is D2, I'm going to make a note for myself that that's the opposite. The adjacent is my D1. So to find the first displacement and second displacement, which functions can I use? Sine and cosine. So we'll start off with opposite adjacent, which is our D2, and we know that the sine of theta, that's our theta in there, is equal to, this is our resultant here, opposite D2 over the resultant. Okay. So to solve for D2, it's pretty easy because the sine of theta times the resultant is going to equal D2.
What is the black arrow going to?
Ah, wait, this one or this one?
What are, yeah.
Okay, that's my little mnemonic for not screwing up my opposite and adjacent. You don't have to do those.
Yeah.
That's me going, okay, dummy, here's your angle. Whoops, here's your angle. There's my opposite. There's my adjacent. That's just my own, don't screw this up, Moser. So let's go ahead and plug in values to get a solution for D2. And the sine of 15 times 23.5 meters is going to equal our second displacement. Who has a raw answer? 6.08 meters. 23.5?
Yeah, I didn't see that point on that one.
Okay, sorry. Okay, so now you've got me doing it, 6.08 2247 on and on and on meters. So we're if we take sig figs into account and we only have 2 because of the 15, we're basically 6.1 meters north. So from where we started, we're 6.1 meters north. Now we're not 6.1 meters north in a direct line. How far east did we go? Okay, so we're basically 6.1 meters north is our second displacement. Can't write a D to save my life. But if we want to know how far east we are, which function are we going to use to break apart the vector into its components? We only have 3 to choose from. We're going to use cosine. Because now if we want to figure out how far east we are, then we're going to have to use cosine because that displacement 1 is adjacent to the angle. So we know that the cosine of theta is equal to D1 over the resultant. So cosine of theta times resultant is going to equal D1. I'm going to shrink this. Woo, not the whole thing.
Could you assume that the angle where the D1 results is 90 degrees?
In this case, we are assuming that. Yes, because it is, when we're talking about simple resultant vectors, using the trig functions only works on a 90-degree angle, so we're assuming that that is a 90, yes. Okay, so cosine of 15 times 23.5 meters is going to equal our first displacement, who's got a raw value displacement. So with two sig figs, what do we get?
22.7.
23 meters east. That's okay, is our initial displacement. So did we go farther east or farther north? Way farther east. Most of our travel was east. We worked our way a little bit north, but in fact, we're 23 meters east of where we started. These kind of problems, very often you'll have like a hiking problem or a driving problem. You know, you've driven or walked this many meters, this many kilometers at this heading. How far south of your starting point are you? How far west of your starting point are you? So let's do a quick tutorial on programming the trig functions into your calculator. Okay, so here is one of our difficult TI-30 multi-views. I love these calculators. I like them better than graphing calculators or anything else. When you go to put in a trig function, when you hit the sine button followed by your angle, so 23, well actually for this one it was what? We used sine of 15. I'll show you what you're going to get is it's going to pop up sine 15. It will not close the parentheses. If you put your sine or your cosine, if you put your trig function in first, you have to actually close the parentheses. If you enter this, if you enter sine 15 times, and then we had what, 23.5. Here's what it's going to do. Sine 15 times 23.5. When you hit the equals button, you're going to get the sine of 15 times 23.5, close parentheses. Not the sine of 15, close parentheses, times 23.5. So, because half the time I'm too dumb to remember to close my parentheses, I generally put the sine in second. So I will enter it like this. Let me get rid of all my little marks on here. I will enter it as 23.5 times sine of 15. And then I don't have to worry about closing my parentheses. It won't screw me up. And that's actually what you see on here, is that I did 23.5 times cosine of 15 or times sine of 15. Does that help? Was that the problem you were having? Okay, perfect. Okay. You want to practice another resolving vectors together? Yes, no, maybe? You want to work on assigned problems for resolving vectors? And I'll float around. Let's do that then.